Hi, I'm happy to be here and to speak about Morse boundaries of graph of groups with examples of right-angled Artin and Coxeter groups. This here is part 2, which focuses on Morse boundaries of graph of groups. We will study connected components of Morse boundaries of graph of groups. This is joint work with Ilya Fioravanti, and here we consider the case that edge groups do not contribute to the Morse boundary of the ambient group. In the end of this second part, we will see interesting examples where this is different. So there we look at examples where edge groups contribute to the Morse boundary. And this is related to joint work with Marius Gräber, Nir Lazarowicz, and Emily Stark. What is a graph of groups? A finitely generated group splits as a graph of group if it acts on a simplicial tree without inversions and without global fixed points. We can assume without loss of generality that T is minimal, what means that there is no proper subtree which is G invariant. Then the action on the tree is co-compact. And the tree T is called the Bassert tree. The vertex groups are the vertex stabilizers. The edge groups, the edge stabilizers. And the quotient is always a labeled graph. Examples are amalgamated free products, where the quotient is an edge, and H&N extensions, where the quotient is a loop. And in the last talk, we studied examples of right-angled Artin and Coxeter groups, which split nicely as amalgamated free products. And these nice splittings arose from gluing graphs nicely together. This can be described in a way that we have graphs which we get via taking the union of two graphs, where the intersection graph is induced in the both graphs we started with. If you have such a nice situation, the corresponding group splits as an amalgamated free product of the two groups corresponding to the graph we started with, along the group corresponding to the intersection graph. Please ignore this delta 2 here. This should not be there. And then the quotient is such an edge, and we see here that the edge group embeds into the vertex groups. And now in the last talk, we studied this theorem here, which says that if we have such a nice graph decomposition, and if we start with two groups with totally disconnected Morse boundary, and if we have that the intersection graph is contained in an induced subgraph that are prime corresponding to a group with empty Morse boundary, then the resulting group has totally disconnected Morse boundary. And what we see here is that this condition here is now a condition on our edge group. So the edge group has to satisfy an empty Morse boundary condition. And this is crucial for us to get this theorem. And I would like to illustrate this, what is going on here a little bit with the following examples. Remember, we saw what right-angled Coxeter groups are. They are generated by the vertices of a graph, and we have that each generator is an involution, and two generators commute if and only if they have an edge in between. The nice thing about right-angled Coxeter groups is that in the Cayley graph we see a lot of one skeletons of Euclidean cubes. And now we can just glue in Euclidean cubes whenever we see a one skeleton of a Euclidean cube. And if we do so, we get a cut-zero cube complex, which is called Davis complex. And like thinking of these Davis complexes just gives one a very nice intuition for those groups. And if I now speak of a Davis complex of a graph, I always mean the Davis complex of the corresponding right-angled Coxeter group. And now what we did is we studied like nice amalgamated free products corresponding to graph decompositions with arose via gluing nice graphs nicely together. So let's understand what is happening with the Davis complex when we glue graphs together. So here we have two edges, and we now glue these edges along this red vertex. If we do so, we see that this red vertex here corresponds to a Davis complex with just a red edge And we see this edge in the Davis complex of this edge and of this edge. And now the Davis complex of the two paths is obtained as follows. We take a copy of the one Davis complex, and then we glue copies of the other Davis complex along the red edges, and then we continue in this manner. In this way, we get a space which consists of blocks and walls. The blocks are isometric to the Davis complexes we started with, and the walls are isometric to the Davis complex of the intersection graph. And if we delete a wall, we see that the space decomposes into two pieces. And this means that we have here a Coxeter space with block decomposition in the sense of Mooney. Namely, X is covered by a set of blocks which are closed convex subsets. The blocks intersect only if they have distinct parity, and they exist in epsilon such that two blocks intersect if and only if their epsilon neighborhoods intersect. So walls have minimum distance to each other. Now, if we have such a nice block decomposition, we can cover the following. We can now put vertex in each block and can connect two blocks if they are adjacent. And if we do so, we always get a tree. In this case, the tree is only by infinite path. And this tree is a Basset tree corresponding to the definition we saw at the beginning. And so the group acts on this Basset tree in the natural, nice way. The quotient is just an edge. So here we can now study the Morse boundary of this Davis complex. We see that we get a point for this direction and a point for this direction. So the Morse boundary just consists of two single points. And this fits together to the theorem we saw before. We start with two totally disconnected Morse boundaries. So here I should maybe mention that for me, empty sets are totally disconnected. And we end up with something totally disconnected. And this is because walls do not contain geodesic rays which are Morse. So this condition is equivalent to the condition we said before, that it's like in terms of graphs, saying that the intersection graph is contained in a graph corresponding to a group with empty Morse boundary. In this situation, this graph is just the vertex itself, because the vertex itself corresponds to a right-angled Coxeter group which is finite, and so it has empty Morse boundary. Let's study the next example. Let's glue two paths together. Then we get a Davis complex which is isometric to the Euclidean plane. Again, we get block decomposition where their blocks are isometric to the blocks we started with. The walls are isometric to the Davis complex of the intersection graph, which are just two single vertices here. And again, we see that the walls here do not contain Morse geodesic rays. And so we see here that we can apply our theorem. We started with two totally disconnected Morse boundaries and will now end up with a totally disconnected Morse boundary. And this is in this set situation just an empty set. And what you saw before in this slide here is that the Basset tree we get here is again a bi-infinite line. And again here, like this condition that the walls do not contain Morse geodesic rays, in the terms of graphs, we see that these two vertices here are contained in the graph corresponding to a group with empty Morse boundary, namely in this case just the whole graph itself. Finally, let's look at this example. We glue an edge to two paths. If we do so, we get a Davis complex which looks like this. So again, we see the blocks which are isometric to the Davis complexes we started with, and the walls which are drawn red. And the Basset tree is now a tree where we have here degree 2 and here infinite degree. And again, we started with two totally disconnected Morse boundaries, and we end up with a totally disconnected Morse boundary, namely a Cantor set. And that's it again, because walls do not contain Morse geodesic rays. So we see that this condition of the edge group is very important, which leads to the fact that here walls do not contain Morse geodesic rays. So let's make this more precise, what this conditions actually means. And for that, we look at this example here. So this is a hyperbolic plane whose boundary is a circle. And if we now glue a Euclidean half-plane on it, then we lose 2 boundary points corresponding to this bi-infinite line, which is now not Morse anymore. And the Morse boundary here is just the union of 2 open intervals. But now if we just study this bi-infinite line and call it Y, we see that if we forget the ambient space, then the Y, just the Morse boundary of it, just consists of 2 single points. And so it's very important here to understand if we like embed this space Y into the ambient space or not. And so what we say here is that the relative Morse boundary of Y in X is empty. So if we have a proper geodesic metric space and Y is a subspace, then the relative Morse boundary of Y in X, which is the ambient space, is the subset of the Morse boundary of Y consisting of all equivalence classes of geodesic rays that are Morse in the ambient space X. And here is a warning. We can now equip this relative Morse boundary with 2 topologies, namely with the Morse boundary of the subspace topology of the Morse boundary of Y or the subspace topology of the Morse boundary of X. And like in general, these topologies can be distinct. All right, we are now ready to see the main theory. Say that G is a finitely generated group that splits at the graph of groups, such that all edge groups are finitely generated and undistorted in G, and such that each edge group has empty relative Morse boundary. Then we have that each connected component is either a singleton or it is contained in the relative Morse boundary of a vertex group. In particular, if we have 2 different vertex groups, then their relative Morse boundaries have empty intersection. Again, remember the warning. It's important to be aware of which topology we give the Morse boundaries of the vertex groups. We take the subspace topology of the Morse boundary of the ambient group. It can be different to the subspace topology of the Morse boundary of the vertex group. And now what we see here is that this theorem really is a generalization of the theorem we saw before. So in the case we saw before, we had nice splittings of right-angled Artin or Coxeter groups as amalgamated free products. And we had there the special situation that the vertex groups had totally disconnected Morse boundary. And this, like, because we have that all other connected components are singletons, this implies by this theorem here directly that then the resulting group has totally disconnected Morse boundary. Now I would like to say something about the proof idea. Essential is here that we can use the tree, the Basset tree, to describe the behavior of geodesic rays. So if we have an equivalence class of a geodesic ray in the Morse boundary, then like representatives will either end in a vertex group or switch between vertex groups forever. And in the first case, the equivalence class corresponds to a vertex of the tree, and in the second case, it corresponds to a point in the boundary of T. And now what is happening is that we assume that C is a connected component of the Morse boundary of a G. And now in the second step, we just show that if we have 2 equivalence classes in this connected component, then we have that they correspond to the same vertex group or the same boundary point of the tree. So corresponding representatives will like end in the same vertex group or in the same boundary point of tree. And in the last step, one has to show that if a connected component contains at least 2 points, then there is a vertex group such that all equivalence classes corresponding to this connected component and in the same vertex group. Connected components with more than 2 points do not come from boundary points of the tree. So now what is the idea how to prove step 2? If C is a connected component of the Morse boundary, we have 2 equivalence classes in the connected component, we want to show that they correspond to the same vertex group or to the same boundary point of the tree. And here we use the following picture. So if we have two different Morse geodesic ways, like in the description above, and they then we can look at the situation that we find an edge in the tree which decomposes the tree into two different half spaces. And if we have the situation, we find the situation also in the Cayley graph. So for each edge in the tree, we find a graph, subgraph gamma of E in the Cayley graph, which behaves like a wall. So if we delete this graph gamma of E, the Cayley graph decomposes, and we get two half spaces of the Cayley graph, which are here denoted by gamma of H and gamma of H star. And now what we can do is we can study what happens if two geodesic arrays end in these two different half spaces. And now remember that these graphs gamma of E, they do not contain Morse geodesic rays by assumption. And because of that, we know that if we have a geodesic ray which is Morse, then it has to have compact intersection. Like the intersection of this geodesic ray with gamma of E has to be compact. And this is a very strong property. It leads namely to a splitting of the Morse boundary into two closed sets, where these sets consist of all equivalence classes whose representatives end in the one or in the other edge space. And this means in particular that in such a situation, a connected component cannot contain geodesic rays corresponding to these two different sets here. And this implies directly what we want to show. If we have two equivalence classes in one connected component, such a situation like here cannot happen, but we have that gamma and eta have to end really in the same vertex group or correspond to the same boundary point of the tree. So now here's shortly something to step 3. If we have a connected component and it has at least two boundary points, we want now to show that these all members of this connected components like end in the same vertex group. And what is the idea? So if we have an equivalence class in C, two equivalence classes in C, then there is a line connecting them. And by step 2, we know that the end vertices of this line corresponds to the same vertex group or to the same boundary point of the tree. And now the idea is to use the Morse property and the co-compact action of the group on the tree to show that this second case here is impossible. So what we saw now is that if the edge group does not contribute to the Morse boundary of the ambient group, then we can say quite a lot about the connected components of Morse boundaries, which is quite nice, but this condition was very important. So we can now ask a question, what happens if the relative Morse boundary of an edge group is not empty? And the first example one would have here in mind is the example where we glue a 3-path and 2 paths together along those two vertices here. Here, all these right-angled Coxeter groups have Morse boundaries which are totally disconnected. But if we now do that gluing so that we get this 5 cycle here, the Davis complex is quasi-isometric to the hyperbolic plane, and the Morse boundary is a circle. So we started here with totally disconnected Morse boundaries and end up with the connected Morse boundary. This brings us now to surprising circles and Morse boundaries of right-angled Coxeter groups. Here again, it's just a small recap. We saw the 5 cycle corresponds to a circle in the Morse boundary. This is also true for cycles of which are longer. And the 4th cycle corresponds to empty Morse boundary. And now we can glue these graphs together in this way. And by the theorem we saw before, we know that this gives us a Morse boundary which is totally disconnected. And we can now also understand how the Davis complex look like. The Davis complex will have a lot of copies of this graph and a lot of copies of this graph, which correspond to this 5 cycle and to this 4 cycle. And they are glued along these red strips. So we get here a tree of Euclidean and hyperbolic planes. Now what happens here is that these glued Euclidean planes destroy the cycles we got, the circles we got from the 5 cycle and the Morse boundary. Now what do we do? Next, we study this graph here. This graph is just the same graph as this, it's just drawn a little bit different. And now we glue on this 4 cycle. Then the resulting graph corresponds to a group with totally disconnected Morse boundary by the theorem we saw before. Now we glue in this 4 cycle, and again, with the same argument, this graph corresponds to a group with totally disconnected Morse boundary. But now if we glue this edge here, then these 2 vertices are not contained in a graph corresponding to a group with empty Morse boundary. And so here something weird is going on. And indeed, here we see this graph, and this graph has this nice decomposition. All these graphs here correspond to groups with totally disconnected Morse boundary. But in the end, the Morse boundary of the group we get contains a circle. And every cycle has 2 non-adjacent vertices that are contained in an induced 4 cycle. So all of cycles look like this situation here. Another interesting example is the 1 skeleton of the 3 cube, and like Twan told us about this example. It has a lot of nice properties. There exists a quasi-isometrically embedded hyperbolic plane, whose Morse boundary embeds in the Morse boundary of the ambient group. There does not exist a finite index reflection subgroup, whose defining graph contains an induced cycle of length at least 4 without 2 non-adjacent vertices lying in an induced 4 cycle. The group is virtually a finite volume hyperbolic 3-manifold with cusp. And the Morse boundary is an omega Sierpinski curve by a theorem of Chareny and Cordes system. And in particular, it is connected. And that is interesting because of the following decomposition. We can decompose this graph in this way. And similar, like in the case of the tree paths, we get that these graphs here correspond to groups with totally disconnected Morse boundary. So again, we glue here together graphs which correspond to groups with totally disconnected Morse boundaries and add up with a group whose Morse boundary is connected. What is in particular also nice about this example is that we can also look at another nice fitting of it, namely this one. And now if one steers long enough at this picture, one can discover that the Davis complex here is a tree of hyperbolic planes with 3 valence trees as edge spaces. And this is nice because this means that one can actually really think about how the Davis complex looks like. So one can really like draw pictures, and I think this is very nice because this is a very beautiful example where weird things happen, but you can still visualize it. So this is everything what I wanted to discuss today. Thank you for your attention. And yeah, I wish all of you a great evening. Bye-bye.